Introduction to Scikit-Learn. Scikit-Learn is a Python library. It is used for machine learning. Real-life uses include predicting prices, classifying images, and finding patterns in data. With Scikit-Learn, you can easily build and test models. It helps people make sense of data to solve problems. Running the cell now. Let us make sure we have Scikit-Learn installed and import necessary tools. Import warnings and turn off warnings so our notebook is clean. Import the system module, we may need it for pip installations. This is a comment, you must install Scikit-Learn if it is not already installed. This is how to install Scikit-Learn using pip on Windows. Remove the hash and run this line if needed. Running the cell now. This code sets up the environment by importing necessary modules and suppressing warnings to keep the output clean. While there's no visible output, this step is crucial for preparing to install and use Scikit-Learn smoothly in upcoming lessons. It ensures your system is ready for building and testing machine learning models without interruptions. If you get an import error, remove the hash and run the installation command above. Key concepts in Scikit-Learn. Scikit-Learn works with datasets called features, inputs, and targets, outputs. It calls models estimators like classifiers or regressors. Fitting is how models learn from data. Predicting is using the model to make guesses. Scikit-Learn has tools to split data, scale values, and more. Running the cell now. Let us load our first dataset to see how Scikit-Learn datasets look. Import the dataset submodule from Scikit-Learn. This is a comment, we will load a toy dataset called iris. Assign the iris dataset to a variable. Print the type of iris. Show the keys of the iris dataset. Running the cell now. This output shows that the iris dataset is stored in a special dictionary-like object called a bunch. Notice the keys, which include a data for input features and target for labels, illustrating how Scikit-Learn organizes datasets into features and targets. This structure is fundamental for fitting models and making predictions later in the workflow. This shows that the iris dataset is like a dictionary with different parts. Let us look at the data inside the iris dataset. Print the feature names, these describe our input columns. Print the target names, these tell us the types we want to predict. Show the first example input. Show the first target value. Running the cell now. This output shows the structure of the classic iris dataset used for training Scikit-Learn models. Notice the feature names describe the flower measurements, while the target names represent the species categories. The first input is a set of measurements, and the first target is the numerical encoding of the species, illustrating how features and targets are organized for model fitting and prediction. Now you can see what our data and targets look like. How training works. Training means making a model learn from examples. You give the model your features and what you want to predict. The model learns a pattern. When you have new data, predict is used to guess the answer. Running the cell now. Let us split our data for training and testing. Import the train_test_split function to split data. Split our data into training and test sets. Use 20% for testing, and set a random state for repeatability. Show the shapes of the training and test sets. Running the cell now. This output shows the shapes of the training and testing feature sets after splitting the iris dataset. Notice that 120 rows are used for training and 30 for testing, each with 4 features, reflecting the 80-20 split. This confirms the model will learn patterns from most data, training, and be evaluated on new, unseen examples, testing. Splitting your data is important so you can check how well your model does on new, unseen data. Our first classifier, let us train a k-nearest neighbors model. Import the k-neighbors classifier, an easy-to-use model. Create a new classifier object that looks at 3 neighbors. Train fit the classifier using our training data. Running the cell now. This output confirms that the K-neighbors classifier model has been created with 3 neighbors and trained on your provided data, x_train, y_train. The printed object shows the model's configuration, indicating it's ready to learn patterns from the training examples. This step is crucial as it sets up the model to later predict outcomes on new data. The classifier has now learned from the training data. Let us use our trained model to make predictions. Use the classifier to predict the target values of the test set. Print out the model's predictions for the test data. Running the cell now. Here, the model uses the learn pattern to predict labels for new data in the test set. Notice the array lists the predicted classes for each test example, showing how the model assigns categories like 0, 1, or 2. This step demonstrates how training enables the model to make informed guesses on unseen data. These are the predicted types, targets, for each test flower. Let us check how accurate our classifier is. Import accuracy_score for easy accuracy checking. Compute accuracy by comparing real and predicted test targets. Print the accuracy score. Running the cell now. Here, the code calculates the accuracy of our model's predictions compared to the true labels in the test set. The output accuracy, 1.0, means the model correctly predicted every example, showing perfect learning on this data. This confirms that our training successfully captured the pattern for making accurate predictions. This is the percentage of correct predictions on the test set. Example, changing the model. Scikit-Learn lets you try many kinds of models easily. You can swap models with just a few lines. Let us try using a decision tree. Running the cell now. Now let us use a decision tree for the same task. Import the decision tree classifier. Create a tree classifier and set the random seed. Train the tree model on our training data. Predict the targets using the decision tree. Print the accuracy of the tree model. Running the cell now. This output shows that the decision tree model perfectly classified all test data, achieving an accuracy of 1.0. Notice how easily the model was swapped in and trained with just a few lines, highlighting how Scikit-Learn facilitates quick experimentation with different algorithms. This sets the stage for comparing model types to find the best fit for your data. This shows you how easy it is to switch models in Scikit-Learn. Scaling your data can help some models perform better. Import standard scalar for rescaling data. Create a new scalar object. Fit the scalar on training data and scale it. Use the same scalar to transform the test data. Running the cell now. This code standardizes the feature data by scaling it to have a mean of 0 and a standard deviation of 1, which is essential for many models to perform well. Although there is no visible output, notice how both training and test sets are transformed consistently, ensuring the model receives properly scaled inputs. This step sets the stage for fair model comparisons in the upcoming sections. Your features are now scaled. This is important for many algorithms. Let us see if scaling improves performance for KNN. Create another K-neighbors classifier. Fit the KNN model on scaled training data. Predict using the scaled test features. Print the accuracy of the scaled KNN model. Running the cell now. Here, we used a K-nearest neighbors model with scaled data and achieved perfect accuracy on the test set. This shows how feature scaling can significantly improve KNN performance by ensuring all features contribute fairly to the distance calculations. Notice how easily we can evaluate different pre-processing steps to boost model results. Notice if scaling makes a difference in the accuracy. Here is another model, Logistic Regression, often used for classification. Import Logistic Regression for classification. Set up the model. Train the Logistic Regression model with scaled data. Predict with a trained model. Print the accuracy for Logistic Regression. Running the cell now. This output shows the accuracy of a logistic regression model on the test data, achieving a perfect score of 1.0. In the context of this lesson section, notice how easily we can train and evaluate a new model with just a few lines of code, illustrating Scikit-Learn's flexibility for quickly testing different algorithms. It is easy to try different models on the same data. Let us combine preprocessing and modeling using a pipeline. This is a comment. Now we create a pipeline. Import the pipeline utility. Make a pipeline that first scales data, then uses KNN. Train the whole pipeline on training data. Predict using the pipeline. It applies scaling for us. Print how accurate the pipeline prediction is. Running the cell now. This output shows that using a pipeline combining data scaling and a k-nearest neighbors model yields perfect accuracy on the test set. Notice how the pipeline simplifies preprocessing and model fitting into one seamless step, highlighting the power of chaining transformations and estimators for cleaner, more reliable code. This confirms the lesson's intent to demonstrate efficient model building with pipelines. Pipelines help keep your code neat and avoid data leakage. Cross-validation helps measure model stability. This is a comment. Now we use cross-validation. Import cross_val_score utility. Run cross-validation on the KNN classifier with 5 splits. Print all the accuracy scores from each split. Print the average accuracy. Running the cell now. This output shows the accuracy scores from 5-fold cross-validation using a k-nearest neighbors model on the iris dataset. Notice the high and consistent scores near 0.97, indicating the model performs well across different data splits. This demonstrates how cross-validation helps us reliably estimate a model's performance beyond a single train test split. Cross-validation gives you a better idea about the reliability of your model. Let us see where the model makes mistakes with a confusion matrix. This is a comment. Now we check the confusion matrix. Import confusion_matrix function. Create a confusion matrix using the predictions. Print the text to confusion matrix. Display the confusion matrix. Running the cell now. This confusion matrix shows the model's predictions compared to the true labels in 3 classes, with each row representing actual classes and each column predicted classes. Notice the diagonal is perfect, meaning the decision tree made 0 classification errors on the test set. This confirms the model changes can directly impact accuracy, and it's important to evaluate predictions beyond just overall scores. The confusion matrix shows how many examples are right or wrong for each class. For advanced users, let us automatically tune hyperparameters using grid search. This is a comment. Now we do parameter tuning. Import grid search CV for tuning parameters. Set up a grid of neighbor values to try. Create the grid search CV object with KNN and the parameter grid. Train the grid search on the scaled training data. Print the best parameters found. Print the best average accuracy found during cross-validation. Running the cell now. Here, we see the power of grid search in action. It tests different values for the number of neighbors in KNN and selects the best one automatically. Notice that n_neighbors equals 3 yields the highest cross-validation accuracy of about 95.8%, showing how tuning hyperparameters can improve model performance with minimal effort. This highlights the ease and effectiveness of model optimization in Scikit-Learn. Grid search finds the best settings for your model automatically. Advanced, let us create a custom class for a new transformer. This is a comment. Now we make a custom transformer. Import base estimator and transformer mixin to inherit from. Create a new Python class called firstFeatureSelector. Define the fit method. It returns itself and does nothing. End the fit method. Define the transform method. Select only the first column of X. End the transform method. Create an instance of the selector. Fit and transform our training data to select just the first feature. Print the first 5 rows of the new data. Running the cell now. This output shows the first feature values extracted from the training data using a custom transformer we built. Notice the shape is n_samples 1, confirming the transformer selects only the first column as intended. This demonstrates how you can control and customize data pre-processing steps before feeding data into a model. Custom transformers let you use your own data processing steps in pipelines. What happens when you pass the wrong input? This is a comment, now we cause a type error. Start a try block. Try to predict using wrong types for input features. If there is an exception, catch it. Print the type and message of the error. Running the cell now. This output shows an error caught when the KNN model receives data in the wrong format, strings instead of numeric values. Notice how the message clearly indicates the issue lies in non-numeric input, reinforcing the lesson that models expect numeric data, and proper error handling helps identify these issues gracefully. This highlights the importance of preparing your data correctly before making predictions. Scikit-Learn will throw clear errors if you give it the wrong kind of data. How do you debug when predictions fail? This is a comment, now let us debug inputs. Print the shape of the test input data. Print the first row of the test set. Running the cell now. Here, we're confirming that the test data fed into our model has the expected shape of 30 samples and 4 features each, matching the original dataset structure. Inspecting the first row helps verify the actual feature values the model will predict on. This step ensures our inputs are correctly formatted before moving to predictions. Check shapes and data types if you run into prediction errors. Best practices. Always split your data into train and test sets. Scale your features before using some models, like KNN or Logistic Regression. Use pipelines to combine steps. Tune model parameters for best results. Understand errors using confusion matrices. Running the cell now. Mini project, predicting flowers. Let us recap. We will build a simple pipeline to predict flower types using Scikit-Learn. Steps. 1. Use a pipeline for scaling and a classifier. 2. Evaluate with accuracy and confusion matrix. 3. Predict with your own values. Running the cell now. Now let us build the final pipeline and train it. This is a comment, build the pipeline. Create a pipeline with a scalar and KNN classifier. Train the pipeline on training data. Predict the test data using the pipeline. Running the cell now. Here, we've built and trained a pipeline that first scales the data, then applies the k-nearest neighbors classifier with 3 neighbors. Notice that this code doesn't print output yet, but prepares predictions stored in my_preds, which will be evaluated in the next step to assess our model's accuracy. This pipeline approach streamlines pre-processing and classification into one step, making our workflow efficient and easy to manage. The pipeline is trained and ready. Let us evaluate our mini-project results. Print the accuracy of the pipeline on test data. Print a message about the confusion matrix. Show the confusion matrix. Running the cell now. This output shows a perfect accuracy of 1.0, meaning the model correctly predicted every flower type in the test set. The confusion matrix confirms this with counts along the diagonal and zeros elsewhere, indicating no misclassifications between the 3 flower classes. This validates that our pipeline combining scaling and classification is effectively distinguishing flower species as intended. You can see how well your model is predicting classes. Try your own prediction. Enter 4 numbers: sepal length, sepal width, petal length, petal width. Start a try block. Ask the user to enter 4 numbers separated by commas: sepal length, sepal width, petal length, petal width. Split the input string and convert each to float. Predict which flower type this is. Print out the predicted flower type. If anything goes wrong, catch the error. Print an error with your input. Running the cell now. This output shows the predicted flower type setosa based on the user's input features processed through the pipeline. Notice how the model uses the scaled input values and classifier within the pipeline to make a real-time prediction, demonstrating the final step of applying the trained model to new data. This confirms the pipeline works end-to-end, from input handling to outputting a meaningful prediction. Try with numbers like 5.1, 3.5, 1.4, 0.2 for a setosa flower. Well done! You have learned how to use Scikit-Learn basics. Try experimenting with other datasets. Running the cell now. Subscribe for more. Like and subscribe for more practical Python lessons. Let us know what you want to learn next. Running the cell now.